Okay, so it for me it was usually in the edge cases where it has me. So empty lists or zeros in arrays or in array problems. There was this. Okay, going back to an example that I just showed before, encoding the string. I can just go back to my slides. Yes, I can. Yeah, you can see this expand string, right? Now, I was testing expand string using unit cases, using examples like B7, A7, but I didn't realize that if I had B10, because 10 was a two-digit number, that's something I hadn't taken care of at all. And it's something that I only came across while I was using hypothesis. I don't know if that answers your question exactly, but
yeah, no, it definitely does. Like edge cases are hard to find, like test cases are hard to come up with, and I think hypothesis really does do that great job of finding that edge case and simplifying it to like that simple example.
Mhm.
Cool. Let's just wait a couple of seconds for questions to come in.
Also, I don't have the code linked. I'll have that soon up on GitHub. I'm just gonna clean it up and.
Perfect. Would you mind sharing a link on this YouTube video so folks afterwards can find a link to your slides?
Oh yeah, definitely. I can.
Awesome. That'd be great. It doesn't look like any other questions are coming in. Can we give Suhas a round of applause for that fantastic talk? Thank you so much.
All right. Thank you for listening. And yeah, thank you, Chippy, for having me here.
Awesome. So next up, we're going to have Joey and Andrew. Just give us a couple of seconds while they get set up. Thank you. All right, Andrew, got you on. Joey, have you on? And I have a screen sharing on. Awesome. Do you just want to give a shout out on the mic just to make sure everything's working?
Yeah. Can you hear me?
Yeah, I can. Joey?
Oh, yeah, sorry. Am I good?
Okay, perfect. Yeah, we're good to go. Andrew, Joey, take it away.
Sounds good. All right. First of all, thank you everyone for joining us remote today, and to Chippy for organizing this. So this talk is Deep Learning Models for NLP. I'm Andrew Johnson. I'm an NLP data scientist at ReviewTrackers here in Chicago. So I will be doing the first portion of this presentation before handing it over to my colleague, Joey.
I'm Joey Schuringa. I'm a senior software engineer at ReviewTrackers. I'll be handling more of the implementation aspects in the talk.
All right, so natural language processing, sort of like the title says, processing human language. So I guess I don't know necessarily about the breakdown of the audience listening right now. If you're already decently familiar with NLP, maybe this talk won't be something terribly new to you, but I'd like to introduce it, and especially how state-of-the-art deep learning is used to tackle several NLP tasks in as much detail as is possible given the very, very compressed time frame. But so if I'm trying to explain NLP to someone who's less familiar with it, I like to start off with very salient examples because it does affect our everyday life. I like to say, you know, if you've used Google Translate or Siri or Alexa or something similar, you've already interacted with NLP. And so under the hood of those, you would say like, oh, Google Translate, that's machine translation. That's a major NLP task. It used to be done with statistical models. These days, most state-of-the-art machine translation will be deep learning based. Siri, obviously, there's a bunch of different tasks that sort of come together to make that work. But one example is automatic voice recognition. So like speech to text, similar technology. And Alexa or other similar digital assistants, one component of them would be dialogue generation. And so actually the tasks I'll be going in more detail later in this talk will not be any of these I've listed here, but they still fall under the same umbrella. And so, like I mentioned, how deep learning is used for machine translation, I wanted just to start off by establishing a sort of the distinction between several terms, which some people might be confused about, or some people might think are completely synonymous, when in fact they're related, but they're more hierarchical in nature. So artificial intelligence is basically just making a computer behave in a way that seems intelligent. However you slice and dice that to achieve that goal can still be called artificial intelligence. So even if I, sit down, spend 5 years of my life coding a bunch of like if-else statements, but the outcome seems intelligent, you could say that's AI. But as you sort of go in on this circle chart, it's more specific, your approach to achieving that goal. So machine learning, the keyword there is learning. The idea being you have this data, and your algorithm is able to process that data and achieve your task, maybe find patterns in the data. So then within that, there's deep learning, which, so this is leveraging neural networks. So the idea is, it's based off of the neurons in a human brain. So the sort of corresponding part of a neural network would be a node, and those nodes are arranged in layers, which is where you get the term deep. That makes them deep. So it's that sort of common understanding established. Currently, one of the big state-of-the-art models for NLP is Bert. That's an abbreviation for, it's quite a mouthful, bidirectional encoder representations of transformers. Won't get into that, but sort of the big thing right before Bert was actually called Elmo. So you see NLP for some reason recently has a big Sesame Street vibe going. But Bert is from Google AI, came out about a year, maybe a year and a half ago. And it sort of does several things very well, which is why a lot of people have been using it. One thing is that it's pre-trained on just massive amounts of data. So, again, deep learning requires training data. And if I have some task I want to achieve, getting all that data for my task to train a model from the ground up takes a lot of time, takes a lot of data. Bert, by nature of being pre-trained, you don't need as much to get it going. So maybe it already has this base knowledge of the language and the task, and then I just toss in a little bit of my own data to, they would call fine-tune it. So that's a big benefit. And then it's also quite easy to use for multiple tasks. So maybe whereas before you would have quite different architectures from one NLP task to another, Bert itself is the majority of your architecture for these various tasks, where all you need to do is maybe add one layer at the end to make it work for that specific task. So it's almost like Bert has given you this nice, big, delicious chocolate cake, and you just have to decide whether you're going to put a cherry on top or a strawberry or some whipped cream, you could say. And then I just wanted to highlight the performance of Bert and similar models. This is the Glue leaderboard. So it's updated. Well, let me explain it. So these are all various different NLP tasks and different models' performance on them. But this is sort of the average score across all of their tasks. So you can see Albert, that's derivative of Bert. Struck Bert is like Bert. T5 is also Google AI, so that's sort of building upon their Bert model. Roberta is from Bert. So, and actually Ernie and like Electra, those could be similar to Bert for all I know. I'm not familiar with them because this is updated as new models come in. But I'm just trying to highlight that Bert and related models are really just dominating these various NLP tasks. And you'll see that us mere mortals are only ranked 12. So that might seem kind of like, I don't know, maybe jaw-dropping that all these models are beating human performance. But with that in mind, they did sort of update some of the tasks to make them more difficult for machines compared to humans. So the Superglue leaderboard, which is newer, at least for the time being, humans are still #1 on that. So moving on. I also just wanted to toss in a slide where someone who maybe wants to get into NLP or deep learning but doesn't know sort of libraries to use or where to start, maybe these would be some references. So you might already be familiar, but Python has a sort of a nice array of machine learning libraries right off the bat. PyTorch is fairly easy to get into. TensorFlow is used widely. before it was TensorFlow 1.0, which you could argue is kind of more difficult to get into because it's sort of builds a symbolic graph and then executes it. But TensorFlow 2.0 has eager execution, so it might be more intuitive for some to use. Keras these days can kind of come packaged together with TensorFlow, so it's easy to use Keras if you already know TensorFlow. And then there's MXNet, which I've used a bit as well. Personally, I'm not as big a fan of it, but it's sort of like Amazon's baby. It's their machine learning library. So then for BERT itself, I would highly recommend Hugging Face. They've got implementation of not just BERT itself, but all these other models, Roberta, Albert, not just in English, but all these different languages, well documented. So I would recommend Hugging Face's implementation of BERT, which is through PyTorch. And just some other things if you're not familiar. Spacey is great for a lot of different NLP tasks. It's fairly easy to use and it's pretty efficient. So like maybe I have a string that's just a long sentence. I could use Spacey to automatically break it up into different sentences, different words. I could get the part of speech of those words. I could lemmatize those words. So like I could, normalize running to run or like went to go. All of that can be done very quickly, easily with Spacey. And then scikit-learn, that's great for other machine learning tasks, dimensionality reduction, clustering, what have you. So just wanted to sort of lay that out there. So then I would like to go over how you might use BERT for some NLP tasks. That's kind of weird. You're supposed to be seeing an image here. I don't know what happened, but that's not a huge deal. Basically, just imagine here there's a box that says BERT, more or less. So for one NLP task is named entity recognition. And when I first was introduced to the task, it sounded kind of boring or not that important, but I just wasn't appreciating how actually prevalent it is. So I'd like to start off with an example of, let's say you have Google Home or a similar device. You want to be able to tell that device, play Hangman versus play jazz versus play the Smiths. So, in one case, Hangman is a game, jazz is a genre, the Smiths are a band. So it needs to be able to recognize that distinction. And so this example here, it's got play, rock, and the image would have like ... So you have the rest of your tokens, and then maybe the final token is please. So for every token, it needs to predict across your entire tag set. So maybe our tag set, let's say, is game or genre or band or O for other. So it's not a named entity at all. So ideally, our model will say, okay, for play, the most likely tag is other, rock, and roll. Each of those tokens should be predicted as genre. And there's a little bit more nuance that goes into most NER systems in that you want to be able to distinguish rock and roll, where each of them are three separate named entities that are a genre, versus rock and roll, they should all be combined. Rock and roll itself is one named entity, but that's just sort of a little subtlety with the tagging system. But so that's named entity sort of in a nutshell. And so you have your BERT layer, which takes in the text at the bottom, and then you just have this layer at the end to predict over every token. Now, another task is classification. So maybe we have a sentence, great burgers, ... milkshakes. So like maybe it's great burgers and wonderful milkshakes. So here what we're saying is, this input, this entire sentence, refers to the topic of food as opposed to, say, service or value or what have you. So the difference here is that instead of running this prediction over our tag set for every individual token, we're only running it like once for that utterance or sentence, whatever our input is. So this whole thing, great burgers and wonderful milkshakes, should be classified as food. And then the third task I'd like to introduce is sentiment analysis, which actually in this example is basically the same under the hood, just your tag set is now positive, negative, maybe you could have neutral as well. So again, great burgers and wonderful milkshakes, that should be predicted to be positive. So what that really has is two different BERT architectures, or BERT with sort of two different applications, the sequence labeling and then the sort of classification approach. I should point out, though, that if you're just going to use this approach that I outlined for sentiment analysis or classification, there would be some error modes, or at least depending on what input you'd expect. So I just wanted to acknowledge that if you had input that says something like great burgers, but the service was very slow, already you're running into some difficulties because, one, that's two different sentiments. Burger is positive sentiment, service is negative sentiment. So if you're looking at that entire input and trying to say this whole thing is positive or negative, you're basically losing out on half of the information. So that's just something to consider. There is a subset of sentiment analysis that will tackle problems like this. It's sometimes referred to as target-based sentiment analysis. So if this is something you yourself want to tackle, maybe you could do a literature review on TBSA. Same thing with the category or similar thing. So this sentence does in fact refer to food, but it also refers to service. So maybe we want an approach where it's not just one tag, like it can be food, but it can't be any other. Maybe we want an approach where it can be food, but it could also potentially be service or value or whatever. So that would be multi-label classification might be one way to get around that. So just sort of having introduced you to these three tasks, NER, sentiment analysis, and classification, I wanted to highlight how ReviewTrackers data might be using these tasks. So this is an actual review for an actual company. Came in through Google, food was good, et cetera, et cetera. So what we might call this is keyword extraction, but one way of thinking of it is as a type of NER, where if it's a keyword, if it's an important word, then it's a named entity, and otherwise it's not a named entity, it's not a keyword. So here, everything underlined has been extracted by our in-house model as a keyword. So food is a keyword, noise level is a keyword. Quiet is also a keyword because it's important, that's useful information to extract, but you'll also notice quiet as an adjective. In the previous example, maybe it wouldn't necessarily have extracted an adjective. So I also want to point out that even though before my example was like genre, music, game, it's really up to you how you slice and dice, how you define your NER tag set. So this is quite different from that previous example. Another very common NER tag set, if you're maybe processing like news text, might be a person's name, an organization name, or a location name. So then you can, read through, let's say, all the New York Times for a given day and extract what you want to know about that. In the healthcare domain, they're going to have their own completely different NER tag set. So this is what we have here. So then the next step is applying sentiment analysis. So for each of these keywords, you can see it's underlined in green or red for its sentiment polarity. So food is good, keyword food is therefore positive, noise level is unbelievable, so noise level sentiment is negative. So this is, as you can see, target-based sentiment analysis because it's more fine-grained than just predicting it across the entire sentence. And then so finally, on top of that, for each of these keywords, there would also be a class predicted, right? So maybe food would be in the food category. Noise level might be in the sort of a category about the ambiance of the location, right? And so you can see that here, this sort of highlights actually all three, the keyword extraction, the sentiment analysis, and the classification all aggregated together. So this would actually be data, for a given location over a given time period, all the dimensions of the keyword. So maybe clean was mentioned positive 57 times, and that's in the atmospheric category, versus loud mentioned in 28 times, and that's negative sentiment. So you can see, like maybe if you were just looking at that, you would say, okay, maybe it's somehow performing NLP to get me this table that you see here. But under the hood, you could really break it down into these three tasks I outlined before. So I believe, yeah, that's all I had about my part of the presentation. I'll hand it over to Joey, and maybe we can take if there's any questions at the end.
Cool. Yeah, so I think one of the biggest things that we've run into while working with NLP is kind of managing how the models that we generate are stored and how we deploy them and how we test them. So I'm just going to go over that very quickly. So what we've kind of moved to now Before we actually had our models getting pulled down by S3 every single time we deployed, that was kind of getting unwieldy, and it was difficult to like quickly push changes out because we'd have to pull down 3 gigs every time. So what we've done now is our models are still stored in S3. It makes it really easy to update by hand whenever Andrew has anything new for us to use. But what we do now is we have a Jenkins job that will grab from S3 and put them into essentially a Docker volume, we use Docker Swarm for managing our containers. So there's a plugin for that called Cloud Store. So we'll store those in Cloud Store and then attach them to our containers at runtime. So basically what ends up happening is they're all inside the file path for each container that needs any of the AI models. And it allows us to very, very easily, with the click of one job, swap our new models in and out in case anything goes wrong or if we need to change something. And it's really nice. And so testing is very, very simple for the most part. It's kind of what you'd expect. Model updates, we run through our integration test suite. It's nothing fancy, just typical integration test stuff. This is really nice. I mean, it's integration tests. It allows us to, we've had issues before where we've updated our models and our unit tests